right. Hey, everybody. My name is Jesse Wilson. Am I here? Am I audible? Am I audible? Yeah. Hi, I'm Jesse Wilson, and this is called Deconstructing OkHttp. OkHttp is a library for making HTTP calls. It's old. It predates Ktor coroutines. It's older than Kotlin 1.0, but it's not older than the ancient imaginations of Kotlin. It's secure, fast, and simple. And in this screenshot here, this is my favorite bug report ever filed against any project. The bug report is that in the gRPC project, which serious people use for serious running their entire businesses, there is a bug report that says Netty is significantly slower than OkHttp as the underlying transport for gRPC. And the thing I love about this bug is it's framed as if Netty is like big grown-up enterprise software, and OkHttp is this like silly little thing that the Androids use for their mobile apps. And the thing that we get in OkHttp is it's not the big complicated enterprise thing, but it has a bunch of those same sorts of optimizations and things. And so again, if you look at that bug, it says 2020 that bug is filed, and this screenshot is last week, so this is a open bug. Now, how do we make OkHttp fast, simple, easy to use? It's literally just like by trying hard. I would love to say, here's the one quick trick, but trying hard is the one quick trick. And in this talk, I've got 11 different little case studies of cool, fun things we did in OkHttp to make it a better library. Some of these things will be useful for you to take away in how to build your own software in some better way. And some of them will just be me flexing and saying, look at this cool thing we did. I'm so proud of it. And most of it is just the insides of this library. There's a little bit about how it would impact how you use it. But the talk is all just sort of like looking inside of the machine and saying, how is this actually working? I'm going to start out by talking about TaskRunner. Some context on TaskRunner is that it predates coroutines as a problem to solve. And maybe one other piece of context is that OkHttp is a library that does not depend on coroutines on purpose. We could potentially change that in the future, but we have a very deep and long commitment to our Java language users who will not have access to coroutines. And so we want to solve this problem without coroutines, and that makes it like extra annoying. When you do stuff in OkHttp, for the most part, it's just an API where you say, give me something, and it gives it back. But in TaskRunner, we want to do things asynchronously, and there's just like a bunch of different stuff where we'll do something asynchronously. One example is that on a WebSocket, you can say, like, send this message to the server. That call to send the message just queues the message up to be sent. And then it will happen on an I/O thread. And so the consequence of that is that you can post messages on a WebSocket as fast as your application needs to, and they'll write to the outlying socket basically as fast as the network can keep up, which might be a reasonable delay. And one more piece of WebSockets here is that you can configure a ping to keep the socket alive. And so you can say, every 5 seconds, just tell the server, I'm still here. The server doesn't generally care, but all the middle boxes between your phone and the server, or between two pairs of servers, all those boxes are just trying to clear unused TCP connections that they think are no longer used. And so if you keep this ping, it will prevent those things from garbage collecting your TCP socket. There's a couple of other consequences where we're talking on a socket for a WebSocket, and it's that the socket itself is not a concurrent type. You have one thread writing to the socket at a time. And so we have a concurrency problem, which is that we potentially are enqueuing lots of writes against the same socket on multiple threads. We want to transmit them on the same thread. And then simultaneously, your program may have many, many WebSockets. A server, for example, could have thousands. And so the first easiest solution, this is where you should stop if you don't want to be extreme, is you just use a single shared scheduled executor service. And I got a diagram here where you have a thread, and you just schedule the work. And so in my little animation here, every 100 milliseconds or something, a different connection is sending out a ping. And I'm imagining in this example that I've got 3 connections to purple.com, pink.com, and blue.org or something, and they're just pinging each of them. And the fact that each of them is pinging, say, every 3 seconds means that there's a ping going out every 1 second from the different connections. Those 3 connections aren't necessarily coordinating with each other or interested in each other at all, but we have one scheduled executor service, and so we send all of them on that thing. And then we can imagine that the purple service is getting a denial of service attack from the new Grimace fries at McDonald's or something. And so that ping takes a really long time. And then the other pings are not transmitted when they're scheduled to transmit, because they're just waiting for that thread to become available so that they can do their work. And the TaskRunner abstraction in OkHttp's job is to make the trains run on time. And so, yuck. So the second one is a much simpler solution. We just have 3 threads, and so each thread is managing its own thing. And what's really nice here is that if the purple service is delayed, it's delaying only itself, and it has to delay itself anyway because we can't send that 3rd ping while the second one is still completing. So this is a great solution. Again, probably stop here, but in OkHttp we want to do better, and what we want to do really is accomplish the same work with less resources. And in the case of threads, every thread is both a consumer of memory in your process and also effectively a place where scheduling needs to be managed by the kernel. So we're going to do a 3rd one. This is a hypothetical one. What if we have one scheduled executor service to manage the timing, and then a thread pool executor service to manage the execution? And so what that looks like is the scheduler is doing these really fast pulses and just saying go, and then the actual ping I/O work is happening on a worker thread. That's great in this happy case. In the case where purple is slow, we get this really weird thing. I'm going to stop time here, and so the purple task is still holding our worker thread, and the pink task has said go send a ping. And so what our thread pool is going to do is it's going to allocate another thread and send its ping on that. And then what's going to happen is the scheduler is later going to say, oh, it's time for our 3rd ping on the purple connection. And this one is in big, big trouble, because the only correct place to schedule this is on that 1st worker thread. But the thread pools don't know about each other, and so it's going to incorrectly send it on the idle worker thread. And now what we have is we have 2 threads concurrently working on the purple socket. In this case, I'm saying way, as if it's waiting for that socket to be held. But this is basically a disaster of an implementation, because one socket connection is currently holding 2 threads. And if you imagine that ping taking an even longer time, that is your process crashing. That is your server going down. And so that's really bad. And then it ultimately completes. But one slow operation should not kill your server. So super yuck. So this is where we were when we were thinking, how can we make our task execution stuff use fewer threads in OkHttp? And so we had this idea where we would have a coordinator that is in charge of both scheduling and execution, and its responsibilities would change. The system is resourceful, which is that if it's running a task, it will create a new thread to be its successor. And the rule of our TaskRunner abstraction is that it will scale all the way down to 0 threads. So if you're not actually using OkHttp for anything, even if you were in the past, all of the threads that it's allocated will eventually just time out and close themselves, or exit. So in this case, we had the line painted white, and we're about to start this first ping. I'm drawing the little thin. We're about to start that ping. And I'm going to create a second thread. The first thread's job had been the coordinator, the scheduler thread. And now we say, thread 1 is going to change responsibilities. It's no longer the orchestrator. Instead, it's going to be the executor, and it's created thread 2, it's forked thread 2 to go be the executor. And now thread 1 can do its job. And now thread 2 is back, and it's the orchestrator, and it's time to run that second ping. And I'm demonstrating this by showing the line is white. So the white line means you have you have scheduler responsibilities, and so we just ping pong back and forth which of these two threads is responsible for scheduling. And there's always at least one thread that's responsible for handling effectively what the next job will be. So they're ping-ponging back that responsibility. That case is relatively straightforward. It's the case where the one ping takes a really, really long time where things get interesting. So we start out in the same situation we were in before. We're ping-ponging back and forth, and the scheduler responsibility keeps moving. And now here we're in a situation where we want to send that pink ping, and we don't have we have to create a new thread to be our new scheduler. And so we create a new thread. The scheduler's job is just you're in charge of future jobs from here on in. And so that happens, and then when that new scheduler, when that new thread comes online, it can designate thread 1 as the scheduler again. And so what ends up happening in our system in OkHttp is that we temporarily use 3 threads, but the steady case of this thing, it will be probably 2 threads. And in this example, I'm showing 3 simultaneous things that it's babysitting, but this could be hundreds of things that it's simultaneously babysitting, all sort of flattened down onto a pair of threads. The one other thing I think is interesting to show here is that the third purple ping at the top middle of the screen, that one is not locking or holding any resources while it's queued, because our TaskRunner abstraction organizes tasks by the connection that they're targeting. One other thing we did in this API is we built it out 100% to support testing. And again, if you've been using coroutines recently, the testing story is fantastic. You get your test coroutine scheduler, and your tests can simulate time. I absolutely love it. We had something similar, not as nice of an API, not as powerful in OkHttp just for this system, where we could write tests that do things like this, where we're ping-ponging between threads, but our test cases themselves simulate the clock, and they're single-threaded and deterministic. My advice for this first item is just that you can do things. Like if you don't like what the Java built-in scheduler executor service is, or some built-in Kotlin API, you can just write your own. Almost none of the interesting stuff in the standard library is like using some magical platform feature that you can't get access to. You can do your own cool things. The caveat, the other side of this though, is that this thing is this specificness of our TaskRunner abstraction is dangerous, because the number of resources that we're holding changes as the world outside of your program changes. So you saw that we were potentially using 1,000 threads to do some job, and then some service far away gets slow, and suddenly we end up using potentially 2,000 threads to accomplish the same work, because all these things where we were able to collapse multiple tasks onto the same thread suddenly can't. And this is sort of like the danger of building systems that do resource consumption dynamically. It's very optimistic, but when things do go sideways, the operations of it is scary. All right, sockets. So I got 11 of these things. I'm going to try and run through them faster than that one. What's a socket? It's how 2 computers talk to each other. Where is it used? So in HTTP 1, HTTP 2, we use TCP sockets on everything. In HTTP 5.2, the newest one, you can create a socket as a way to upgrade a HTTP connection. So you can talk to a server and then get a socket layer abstraction between a pair of servers. And so this is the Java socket API, and it represents a TCP connection. And there's a whole bunch of TCP stuff related to Java's socket. We recently introduced a new socket interface in OKIO that is wildly different in terms of its design. It has 2 streams and a function to cancel itself. And so why would we build a different shape of interface for this problem? If you look at the Java IO socket interface, or I guess it's an open class or something, it's got a whole bunch of different functions. And those functions both give capabilities to the people who are calling that API, but they also constrain what implementations are possible of that interface. And so the Java IO socket API really just has two sort of core implementations, the TCP one and then the TLS one that wraps the TCP one. Here's the OKIO socket, and we just get to do more stuff with our socket interface. And doing more stuff with one interface is, it's kind of cool. The part I really like about this is that some of these are wrappers. And so we can wrap TLS around a TCP socket, and then we have a TLS plus TCP socket. But because these things are all implementing the same common interface, we've created an opportunity for ourselves to potentially do other interesting layering. So, for example, we could layer TLS on top of an HTTP upgrade socket, or we could layer a quick stream with a different socket abstraction on top of it. So one more thing over the Java I/O socket versus the OKIO one. The Java socket API is good, and it's old, and it has this close function that's kind of close in terms of resource management, but it's also cancel. And so you can take somebody else's socket that they're using and cancel it, or close it asynchronously. And that will also free up resources. And I think it's a really awkward API to conflate closing something, which is resource management, from canceling it, which is whether I care about the resource and run this to completion. This is another thing where I think coroutines is just amazing because they've got cancellation as a first-party, built-in part of the system. One more part of all of this is the socket interface we've done in OKIO can be backed by a fully in-memory data structure. We have a function called in-memory socket pair. And one thing I'm really excited about is we can do potentially HTTP layer test cases that never even talk to the operating system's socket API. And so you can make tests that run dramatically faster because you're never doing that the kernel calls, system calls. All right. Item 3 is extensibility. Extensibility is an escape hatch. We don't have to add a ton of features to get a ton of users. And so, again, in that gRPC example, OkHttp can carry gRPC, but it can carry gRPC because we just built the right places where the gRPC team can plug in their behavior. I want to talk a little bit about our philosophy of designing a big, complicated surface like OkHttp. You always start out, every single library in the entire world is called a lightweight something. It's like a super light, this is the lightest thing, and then you end up following the, like it's a simple object access protocol, and you're like, yeah, SOAP is so simple, and then you just keep adding features to it. What happens over time is that you extend that library to meet the needs of all of your friends and all of your customers. And pretty soon you have a big library. And what's tough about this is that every user of this library is getting way more than they want. And so I think of extensibility as being this API design hack where you can maintain a small library and still satisfy everybody's needs. Interceptors is the first of our 3 different extensibility features I want to talk about today. Some quick OkHttp history. In 2013, we wrote that OkHttp 1.0 was out. And then 3 years later, 1 year later, we added interceptors as an API that end application developers could use. And then 2 years after that, we dramatically re-implemented OkHttp itself to use our interceptors as its own implementation. And so if you open up OkHttp and you say, like, how does it work? The entire library is just this stack of 7 interceptors. And the first one is just all of the application interceptors that users write. We have one for retries, bridging, caching, connecting, and then we run all of the users' network interceptors. And then finally, we call the server. And so OkHttp's own architecture is just a bunch of interceptors that apply different processes to the HTTP calls and responses. I think it's really weird that this thing that we built as an extension mechanism became the internal architecture of the library. And we didn't design it to do that. It just happened. And I think it may be a testament to the fact that our extension API was good enough that it could carry the whole library. Yuri Shimke, who did the excellent talk on Remote Compose yesterday, has been working really hard on OkHttp stuff for years. And he recently landed a fix where our interceptors can do way more than they ever could. So for example, you can write an interceptor that changes what your DNS is. And so you could potentially have an interceptor that uses a different DNS if you're talking to your company's server versus if you're talking to your ad network or something. All right. Event lister is another extension mechanism. And so in 2015, somebody came in and said, hey, could you add some logging? And Jesse says, logging? What for? And they say, I'm trying to debug why your response isn't cached. And I say, you want an observability system. And they said, as long as I can tell why this response isn't cached. And I say, we just shipped event listener. Hooray. Oh, by the way, this conversation has taken 5 years. And the person who I'm talking with says, I retired from programming 3 years ago. All right, so the first instinct when we're building something like observability is just like, let's just add some logs. I think logging is the worst form of observability. It's invisible to operational health, business health. You never have the context you want. It's expensive. Does anybody here work for Splunk? Those people are driving like very nice cars. And it's insecure, so anything you put in your logs is either PII or incomplete. There's this wonderful blog post, Do Not Log, and it should radicalize you. It radicalized me. Event listener is like logging, but good. And so anywhere we would perform logging, we instead have a function that passes all the stuff we write to the log instead. So if we're about to do a DNS call, we just say DNS start on our event listener. And then it's somebody else's problem to decide if that's going to go to the log. We have logging event listener, or if it's going to go to the Datadog system or some other observability system, or if it's going to plug into some business metrics. Again, we are hooking into everything, and we can even do business layer things like the TLS handshake slowed down, and then our company is making less money. When we introduced Event Listener, it was another giant OkHttp internal refactoring. And one thing I found really interesting about this was when we said, we should have exactly one place where we do a DNS lookup so that we can have our log calls symmetric, it actually forced us to tighten up the implementation and make it so that the implementation sort of lives up to the ideals of the events that we publish. I want everybody here to go into your applications, go into your libraries, add event listener interfaces, and then start using them, and change how you do observability. And then one more thing that I find really, really excellent is that you can use event listeners as test facets. So if you want to say, I want to make sure this side effect happens, or I want to make sure the side effect doesn't happen, you can write test cases that say things like, this OkHttp test should not make 2 DNS requests, and we can fail the call because we log events when those DNS things happen. Tags. So OkHttp will let you attach arbitrary data to your HTTP calls. And the key of each arbitrary data is a class. You can use this for more observability. You can attach trace IDs. You can use it to basically wire data from different systems. If you write an OkHttp interceptor, you can read the retrofit metadata that it injects in your interceptor off of a tag. There's an invocation tag, and you can say, what function was I calling when this HTTP call was made? And then you can use it to do things like put application-specific data into your calls. Our implementation, the sort of most reasonable thing would be a map. We didn't do that. We were like, can we do better? Concurrent hash map is this thing that's like kind of wonderful and also just like a really, really powerful thing. Concurrent hash map is like a concurrent database, and every instance of it has a lot of really powerful features for like sharding your key lookups, which you probably don't need in many cases. In the case of our tags, our target number of elements is probably about 0, and it may, in big extreme cases, might have like 2 keys in it. So we borrowed from coroutine context as our implementation strategy for our tags map. 2 implementations. One is just there's no tags, and another implementation is I have a single tag and then a reference to another tag's implementation, and that is recursive. It's a little linked list of map entries. And so that's our API. One thing that's really interesting here is that the empty tags and linked tags objects are immutable. And so there's one instance of empty tags in the entire process. Every time you create a call, it just reuses that exact same instance over and over again. And then when you create a new tag entry, it just puts a linked tags there and points at the empty one after it. This is the 30 lines of code that we use to achieve maximum concurrency, where we swap out an atomic reference of tags with a new instance. That code is like kind of scary, but I also think it was probably, it's also kind of fun. And so we get just, the whole tag system is about 150 lines of code, and what we yield from it is that adding the tags feature to OkHttp costs you nothing if you're not using it. All right, so HTTP URL. Imagine that you have a URL for a conference talk. This is the code that you would write to build that URL string using Java's URL API. And I hate it. You might say I hate it so much, it radicalized me into creating an HTTP library and maintaining it for 13 years. This is the API from OkHttp. I think it makes sense. The HTTP URL API has a bunch of responsibilities. It kind of looks like it's a string, but it has a lot of responsibilities to take that string, canonicalize it, normalize it. Here's some sample URLs. Right now, I'm just focusing on the host name. That's like the most fraught place of the whole system. And when you ask OkHttp the URL on the left, it gives you the URL on the right. And there's just like a bunch of weird cases. You can ask for the URL sigma, and it'll give you back, this is the third from the bottom, xn-4xa. It's like surprising. And as an English speaker with Latin characters in my language, I didn't really appreciate how complex this gets. I think that even throughout Europe, we're usually using mostly English characters in our URLs. But I think that the accessibility of the entire internet improves when URLs make sense to people who don't speak English all the time. How does OkHttp implement this? Just with lots of stuff, some test suites and 2 embedded databases. Did I just say 2 embedded databases? 2 embedded databases? Why are you embedding databases in your URL class? There's a public suffix database. And so the question that the public suffix database exists to answer is, which URLs share cookies with each other? And so if you go to google.com in your browser, if you go to maps.google.com in your browser and you sign in, and then you go to mail.google.com in your browser and you sign in, you will already be signed in. That's critical. And so both of those websites share cookies. They share the user identity. And this is possible because the URL itself has a public suffix of .com, and google.com is a privately owned domain name. And so everybody at google.com has to mutually trust each other, but we don't have to trust everybody who has a .com with everybody else. There's a different website called dinedns.com, and you can find such excellent websites as the Cottonwood BBS on DynDNS. And that website and every other website on DynDNS is independently owned and operated, and they do not share cookies with each other. They don't have to have a trusting relationship. And so if you look at the strings of these URLs, you can try and figure out how do they do it? How do the browsers know when to share cookies and when to not, right? Here's the answer. And there's some code that shows it's not trusting. Here's the answer. It's a giant list of domain names that share cookies with each other. And so you go to this website, publicsuffix.org, and it just says, DynDNS, all the subdomains of that are independently operated. Yuck. If you go and build a new website and you don't want your subdomains to share cookies with each other, all you do is you add yourself to the public suffix list, and then you wait 5 or 6 years for all the people's HTTP clients to update to it. In OkHttp, our implementation of it is a 132 kilobyte byte array, with new line separated items and a custom binary search. The PSL, does anybody get my emoji? Yeah, no? Pumpkin spice latte, yeah, okay. So there's a different database in OkHttp called the Internationalized Domain Names for Applications Code Points DB. And the question here is how to process each character in a host name. There's 1.1 million code points, and every character, like the letter A, is allowed, disallowed, ignored, or mapped. Here's some examples of each. The donut emoji is allowed in a host name as far as the IDNA is concerned, whereas the uppercase A is mapped to the lowercase a. And so that means that if you register a website with all capital, if you type a website with all capital letters, it will load the corresponding website with lowercase letters. It gets a little bit more complicated, like the trademark symbol is mapped to two characters, T and M. And so if you go to www.hotrademarkail.com, your browser will load hotmail.com. Weird, right? So this one is also a giant list of code points. And so every single character in Unicode, 1.1 million of them, it tells you whether it's allowed, mapped to something else, whether you should just ignore it like a space character. And even though I hate the domains one, I think this is neat. And my only reason for this is that I can't randomly decide I'm going to go invent a character and add it to Unicode without like a bunch of adults checking on me. All right. So the natural solution for this is a hash map with 1.1 million entries. But can we do better? And so we want to build an efficient way to store 1.1 million mappings. We want it light on memory, fast to initialize, fast to query, and then we want to run in all the places Kotlin runs. I know that OkHttp is not multi-platform today, and it will not be multi-platform ever, but HTTPRL might be. Maybe I should. OkHttp making it multi-platform is hard, but I would like HTTP URL in specific to have that opportunity. And so we take that 1.1 million file. It's a 875 kilobyte text file, but there's only 9,000 entries in it because many of the code points are just grouped into ranges. And so it'll say A to Z, all of the lowercase ASCII characters are allowed. And so that's 26 characters in one row. How cool is that? So our second solution is we take the code points and then we map them into 6 buckets, allowed, ignored, disallowed, and then we either map it with a delta offset, we map it to a specific value, or we say the value this maps to is like 6 characters long, so put that in an overflow string. And so with that strategy, we can pack each range of characters into 6 bytes, and we get a 54 kilobyte database. And I think that's fantastic. We took our 700 kilobyte database with 1 million characters in it, and we got it to 54 kilobytes. And the table looks like this. It's just at offset 0, everything is allowed, whereas at offset 00AO, that's mapped in line to the space character. And that's just 9,000 entries, 1 for every one of those ranges. We can do even better than that because the first 3 bytes of every entry are just the location in the code points list. And if we group them, we basically do some offset compression. We shrink it to 40 kilobytes. But there is bad news, which is if we want to ship a 40 kilobyte binary file in OkHttp, we have a bad time on platforms like JS, where there's no native way for a JavaScript file to include a binary resource. And so what we do instead is instead of using 8 bits of every byte, OkHttp, I'm sorry, I'm starting to cry. Every byte in OkHttp only uses 7 bits. So we pack everything very, very weirdly. And then we express the database as 3 incredibly contrived weird strings. And the neat thing here is that if we want to say, like, what's the offset, what's the mapping for the trademark symbol, we binary search the section's string. We binary search the string by its index, find where we look in the ranges table. we binary search a narrower range in there, and then we look up the value inline. And so it's a 33 kilobyte, it's 33 kilobytes in your class file, and it's about 33 kilobytes as like a JS file. So that's fun. All right, big finish here. I got 3 more. Cache. So OkHttp includes a persistent cache. It has 2 jobs: deciding what to save and how to save it. Our persistent strategy is we have 2 files on your file system, like on your device's file system or your server's file system, for every saved response. One has got the HTTP metadata, and then the other is just exactly what we downloaded from the server. And so the code to set up the cache looks like this. I'm going to make a call to kotlinconf.com, wasmo.com, and kotlinconf.com again. And then I'm going to look at our journal file that keeps track of what is actually in the cache. And so it's got 5 lines of header information, and then these lines that repeat dirty, clean, read, dirty, clean. And so each of those lines is a record of the cache doing something to its file system database. And so when it says dirty, what that's saying is this file is wrecked. I'm in the middle of writing it. Do not read it. But do also, if the cache crashes, go and delete my waste behind. And so we have that. And then clean means I have just produced a fresh cache entry for you to use. The metadata basically looks like the HTTP response headers. And then we have to do some extra work to keep the TLS stuff. The body is just whatever you downloaded. And so the cache itself is relatively straightforward, but the implementation is hell, because file systems are hell. If you watched Philip's talk today, file systems are hell. There's just so many different things that can go wrong. On mobile in particular, like the disk fills up, and the last thing you want is like my device's disk filled up, and then suddenly the network stopped working as a side effect of that. That's like a really gross contamination where one failure wrecks another thing. So we built our own self-crashing file system. It takes OKIO's in-memory fake file system, and then we have our own faulty file system. And so you can say, hey, faulty file system, I want to schedule a delete failure. So the next time somebody tries to delete this specific file, don't let them. Just throw an exception. And so there's all sorts of different places like this where this could happen in practice. A completely absurd one is you can fill up your drive, and then you can be unable to delete files because your drive is too full. That feels unfair. So our cache's job is basically to play hurt. So even if the file system goes away, the cache tries to be well-behaved. It's going to have a much lower or none hit rate, but your network calls are going to still work, and all the code that's talking to the cache is just going to observe bad cache hit rates instead of observing I/O exceptions or other failures. So one extra hazard is Windows exists, and there's this bug I allude to where Windows refuses to delete files that are open for read. And a hypothetical example you could imagine is you go to ziglang.org and you read it from the cache. And so there's something that's reading that website, and then you realize that you're at KotlinConf and you should not talk about Ziglang, so you evict the URL from your cache, and then your process crashes. And so we have this hazard, which is that we want to make sure that even if we were reading that file, we still want to ultimately delete it. And in Windows, as soon as you start reading a file, Windows is like, I will not let you delete this until you're done reading. And we have stuff in our cache to mitigate that, but it's just so ugly. So my advice to you is use a database. SQLite exists, Postgres exists. There's databases are good. The file system is the worst. And then if you must, Atomic File or OKO's file system are your friends. All right, TLS. So Java's TLS APIs are bad, and instead of getting my little pink marker out and circling all the bad things, I've just presented them to you in a handy table here. Probably the best one to highlight here is the second to last there's a constant called IP address. The I is lowercase, the P is uppercase, the A is uppercase. I just find this so gross. There's this quote, while everybody talked about the weather, nobody seemed to do anything about it. And I feel like in Java TLS land, it's like everybody complains about how bad the encryption API is, but anybody doing anything about it. And so in 2018, we added our own little TLS utility library in OkHttp. It depends on Bouncy Castle, and then uses the Bouncy Castle APIs in a way that I find less off-putting. And then 2020, we rewrote a bunch of implementation details in OkHttp so that we didn't have a Bouncy Castle dependency. And so if you're using OkHttp TLS, it's just one Kotlin library. This is what our API looks like. You can create a certificate in memory in Java without any I don't know, without too much yuck, and then create a pair of certificates that you can use to create either an HTTP server or an HTTP client that use TLS. Now, in order to make that magic happen, we have to take this scary thing, which is a PEM file, and just make sense of it. And so OkHttp implements its own PEM decoder and dir decoder and dir encoder just so that we can not have to touch the icky crypto APIs. And I think one thing I learned through this process is that the security APIs are way scarier than the protocols and the math that they encapsulate. I think that TLS itself, it's pretty great. It's simple enough, it is safe, it's extensible in all the ways it needs to be. And then the Java APIs that layer on top of it just make it seem so inscrutable. You're like, fuck programming, just make Claude do all the work for me. All right, sorry. Happy eyeballs. OK, this is my second to last. Imagine you have a DNS hostname. It could resolve to multiple IP addresses for lots of different reasons. And so in this code example, we're looking up the thing, and we're printing 3 addresses for kotlinconf.com. And in this imagining, there is a yellow IP address, a green IP address, and a blue IP address. And right now, I want everybody, who wants to connect to the yellow one? Who wants to connect to the green one? Everyone wants to connect to the blue one? All right, excellent, blue wins. OK, so let's see where those IP addresses are in the world. The blue one is in Washington, D.C., the yellow one is in Seoul, and the green one is in Frankfurt. And when we try to do a TCP handshake with these, they're just different distances at the speed of light. One thing that's really cool, you see my animation's annoyingly slow there. That animation is actually 3 times slower than the actual connection. And this map is not the scale size of the Earth. So it's really fast how fast light goes. So which of those 3 IPs do we connect to? In old OkHttp of past, we just pick one. Basically the same as picking a color without knowing any more information. And can we do better? So happy eyeballs is this brilliant idea where why pick one when you can pick 2? Why pick one when you pick all of them? And so we pick one to start, and then we wait 250 milliseconds. And if we haven't got a connection yet, we order another one. This is kind of like how you order an Uber, and then if it hasn't come for 10 minutes, you order a Lyft. It's like that. And so right where we are in Munich, I'm going to send a SYN-ACK packet to Seoul, which I've accidentally picked first. And then if it takes longer than 250 milliseconds, I'll also try to connect to Frankfurt. And so my very carefully choreographed animation shows that it will pick Frankfurt because the connection to Seoul just takes too long. And it ends up that when you have that 250 millisecond delay, you get a good balance between wasting resources and having the good proximity to a fast connection. This is the scariest feature we ever rolled out. When we were beginning on OkHttp, we didn't have any users. We could just hack stuff together. It didn't matter. Now there's a significant amount of the internet that will break if we break OkHttp in an interesting way. And this is the kind of thing where it's like, oh, when we rolled out the OkHttp upgrade to our app, all of our users in China couldn't connect anymore, or we DOS'd our server, or these other things that could possibly happen because suddenly we're multiplying the amount of internet traffic that OkHttp is using by a significant factor. So we just did lots of tests. As you saw, like in TaskRunner, that's that thing I started talking about with the pings. We built that entire abstraction to build testable scheduling, and then that really paid off with happy eyeballs, where we could test these big, complicated connectivity scenarios and have tests that run faster than real time and have tests that run with real DNS. There's a bunch of things we could do to make this even better. I think 250 milliseconds doesn't feel perfect. It's OK. And then we could also potentially remember. So if it turns out that Frankfurt won the race last time, I should probably pick it next time. Last item is upgrading OkHttp to Kotlin. OkHttp started out as a Java language library, and then we saw, the beauty that is Kotlin, and we were seduced by it. And I am so happy that we changed our own implementation to use Kotlin. There's so many things that we need to convert to be idiomatic Kotlin, and OkHttp is not idiomatic Kotlin in a lot of important ways, where we just use Java APIs because that was there at the time. One really simple example of something we've done to improve the Kotlin usability. In OkHttp 4, this is some code to call the Kotlin conf website. And you'll see there's a bang bang on the response body. That's super gross. To explain why, it's possible that response got redirected a whole bunch of times. And it's possible that the redirects themselves are accessible through our API. So you can say, I got a response from calling kotlinconf.com, and then you call .prior response to get another response object. That response object does not have a body because you don't care. But OkHttp's response body type is nullable because it could be that case. And so in Java, this didn't matter because the type system didn't care. We wrote this API where it was like almost always, actually effectively always non-null, but the type system had this one situation where it could be. And in Java, it didn't matter because the type system didn't care about null. But in Kotlin, we make you use the bang bang of shame. And so our mitigation in the new OkHttp 5 is we have a new implementation of response body called unreadable response body. If you attempt to read it, it'll explode. But that means that your code in all of your normal situations just reads much nicer. There's no bang bang of shame. There's a bunch of other backwards incompatible changes for us to consider in OkHttp itself. These are scary, and we're not pursuing them at the moment. And I earlier said I want to make HTTP URL multi-platform. I think that would just be really handy because doing URLs as strings in Swift or in Kotlin.js is just, I can't. So to recap, programming is fun. All of this stuff that we did it because we wanted to make something that was absolutely awesome, and we wanted to make something that would make the internet faster. If we make OkHttp more efficient or use less memory, it actually saves CO2. We can tell ourselves that programming is for the environment. And we're using a lot of tests and testability to solve problems that I think would be harder for me to solve if I was just trying to reason about it. And so a lot of OkHttp's funness is saying, like, can we take this problem, can we make it testable, and then we use the fact that it's testable to just go that extra step. And I really want to emphasize programming is fun. I got this comic here of Hagenbot, the robot that eats ice cream so you don't have to. And Chicken says, but I like ice cream. And engineer says, stop trying to stifle progress. So I'm having a lot of fun programming, and I encourage you to have a lot of fun programming. Thank you.